All right. Last time I defined what's the subspace and gave a couple examples. Let us recall subspaces. So suppose the vector space over field K. A subspace. What was the notation we use for this? Okay, this is S. So S, the subset is called a subspace. If S is a vector space with the operation of B, right? So B has addition, vector addition, scalar multiplication. If S with those operations is itself a vector space, then we call S a vector subspace. I gave some examples last time. So last time we have seen it. For a linear map, they had from a vector space to another vector space. External, and kernel is defined to be just this kernel of a head. I don't use what was kernel. Kernel is the set of all vectors so that a head of B is 0. So the set of all vectors which are mapped to the 0 vector in W. So those elements form a subspace. Is a subspace of B. Bunu gösterdik değil mi? Geçen defa gösterdik mi? Okay. Now, here is another associated subspace to a linear map, which that similarly image of a head. This is called the image of a head. What's that? This is the subset of all images. So this is a subset of W. What I do, I look at all the vectors in V and their images under a head. So these are elements in W, and we claim that this subset of W forms a vector space. It's a vector subspace of W. So what we have, something, let me draw a picture here. I have B here and W here and a linear map. Kernel is something here, kernel of a head. That is the set of all elements which are mapped to the 0 elements. And this B is mapped to, so this is kernel of a head, and image of a head is another subset here. So this is image of a head, Okay, image of a head. A head doesn't have to be onto, right? Some vectors may not be in the image, but what we claim is that if you look at all the vectors which are images of a head, so we have this. Okay, this whole set is not in here. This is a subspace of W. So a vector, a linear map with two vector spaces defines two subsets. One subset of V, one subspaces of one subspace of V called kernel, one subspace of W called image. Now let's see why this is image. Why this image is a subspace. So let me write it here. It's a subspace. How to prove something like this? Well, we have to prove two things. It should be closed under addition and scalar multiplication, right? So let's W1 and W2 be in the images of a head. What I have to show that the sum of these two is also in the image. But we know the following. So W1 is just a head of V1, and W2 is just a head of V2. For some V1 and V2 in V, right? Because they are in the image means that they are images of some particular element. There might be more than one particular elements which are mapped to W1 and W2. I just pick any two of them, okay? Which are mapped to W1 and W2. Well then, W1 plus W2 is what? This is A of V1 plus A of V2. Well, but this is like what? W1 plus W2 is just, since a head is linear, this is just a head of V1 plus V2. But this thing is an element of V also. Therefore, V1 plus V2 is the image of some element in V. Right? Hangisi? Yok. Bu şu eleman V'nin içinde. E W'nin ama bu V1 plus V2 V'nin içinde. V'nin içindeki bir şeyin görüntüsü. Değil mi? Yani ne göstermiş olur? İki vektör görüntüdeyse onların toplamı da görüntüdedir. Değil mi? Here we are using, of course, the fact that A is linear, right, in an essential vector. So this means what? W1 plus W2 is in the image of A head. I have to also show that a similar statement for the scalar multiplication also holds. Let's see that one also. Similarly, if lambda is just any scalar, then lambda times V1, well, this is just lambda times a head V1, but this is just a head of lambda V1, where lambda times V1 is also in V, right? So I took any element in the image, its multiple, lambda multiple of that is just a head of lambda times a vector in V. Well, this vector is always in V because V is a vector space and this is the scalar multiplication operation of the vector space. This means what? This element is the image of some element. Right? Hence, lambda times W1 is into H. So a head is closed both under vector addition and scalar multiplication. Therefore, a head is a subspace. It follows that image a head is a subspace of W. Sorusu olan var mı? Okay. Linear spaces, subspaces, and linear maps are related to each other via these examples, but there's another connection between subspaces and linear maps, special kind of linear maps called projectors. So let me just define what's a projector. A linear map in these examples, if you don't understand something, you should think about it, okay? If you think that, we didn't have to write down, this many lines for this proof, you are not right, okay? One has to write this many lines. It means that you are missing some parts of the theory, okay? Either you have difficulty in understanding a definition or some other statement. So make sure that you understand these arguments, and maybe more importantly, why actually we need these arguments, okay? Yani burada gereksizce iş yaptığınızı düşünüyorsanız doğru değil o, tamam mı? O zaman siz bir şeyleri kaçırıyorsunuz demektir. O yüzden oturup bir daha bir düşünün. Acaba niye bu gerekli? Ben neyi kaçırıyorum diye, tamam mı? They are easy but they are important. A linear map P hat from D to U is called a projection, projected. Evet, projected. Projection da deniyor da. P composition P is equal to P. So if P composition P is equal to P, then we call it a projector or projection. Both are used. Okay. An example. Ya da şöyle diyeyim. Well, we know that image of P, right? This is a map from B to B. Image of P is inside B. Is a subspace, right? Is a subspace of B, right? Its kernel is also subspace, but image is also subspace. Moreover, if B or W is in the subspace, image of P, when it is in the image, then what is P of W? Well, maybe before that, then first of all, W is, since it is in the image, this is P of V, right? For some V in V, and hence, P of W, or P hat of W is just P hat of V, but this is just P hat squared, or the composition, right? This is the composition, but composition is itself is just P itself, right? So instead of this, I can just write 1P, and this is just W. So what we see is the following: P hat acts as identity on this subspace because I took an element in the image, right? And its image under the projection is just itself. Hence, P acts as identity map on its image. Projector, you may consider projector as just, the usual projector. For example, let me draw a picture of a projection. Suppose we are in R3, X, Y, Z coordinates. So this is R3, R vector space. And the projection map is the following. You take a vector in V, let's say, X, Y, Z are the coordinates. We define its projection onto the XY plane. So P is defined to be this way: P of V, X, Y, Z is just X, Y, and then the Z coordinate is 0. So I just look at its image in the XY plane. I just took its projection, okay? Note that what is the P hat of X, Y, Z? Well, this is just P hat of, this is X, Y, 0. What is P hat of this? Again, X, Y, 0, right? So this is a projection, and it's usually, it's really a projection, right? So this is P. X, Y, and 0. Okay? And you see why from this example, P squared is equal to P. If you take a vector, look at this projector, you get a vector here. Projection of this vector is itself, okay? Okay. Actually, any subspace can be viewed as the image of a projector. But let me just skip it now. This is something to think about. Any substance Here, what is the subspace of that projection? It is just the xy plane, right? So in this case, S is the vector space of all planes of this type. Right? So image of P is just the xy plane. Triples like this, x, y, 0. What I claim here, in subspace S of a vector space is V is the image of a projector vector and head from V to V. Nasıl yaparız bunu? Well, let's assume for simplicity V is finite dimensional. Okay, finite dimensional. Take a basis for S. How can we do this? Take a spanning set for S and then delete unnecessary vectors and you obtain a basis for S. First, take a basis, let's say V1 up to Vk for S. Then we know that this is a linearly independent set and it can be extended to the basis, to a basis of V. Extend this to a basis of V, say beta. So I had this many vectors. And I add new vectors k plus 1 up to Vn. Okay. Then define the projector E head from E to V as follows. I just need to tell you what are the images of this projector at the basis elements. So P head V1. Well, this is in the subspace. The image of the projector. It should be in the image of the projector. So P head should act as identity there. So P of V1 should be identity up to P head of Vk. Because projectors, nerede yazık onu? A projector is identity map on its image. So if these are in the images, then P should be identity on those. What about the other ones? The other vectors, K plus 1. Well, I can just send them to 0. Okay. The rest are mapped to 0. Then he has, so let me give check that as an exercise. I think that he had is a linear map, and he had composition. He had just I guess I didn't tell you that any linear map is uniquely determined by its image on a basis, right? Öyle bir şey söyledim mi? Onu belki buraya bir preposition yazayım. So part of this exercise is this proposition. In linear map is determined, is uniquely by the images of elements of a basis. Ne diyorum? Yani şunu diyorum. Aslında moreover for any pre-assigned images of basis elements, there is a unique linear map printing basis elements. Now let me explain what I mean. In the proposition, and let's prove that. I claim two different things there. First one is the following. First one is that any linear map is uniquely determined by the images of that linear map on the elements of a given basis. So I have this linear map, let's say, and we have a basis for B. Let's say, again, for simplicity, I am assuming everything is finite dimension, but actually we don't need that. So take any basis data V1 up, not V1, let's say V1 up to En. Okay. I claim the following. If I know the images of these elements, then I know the image of any other element. So suppose A has I is just I don't know, Fi. Fi doesn't have to form a basis for them. Okay, they are just images of EIs. These vectors can be zero, right? Because maybe these are in the kernel and they are not to zero. So this Fi doesn't have to be a part of the basis already, but just some elements. I don't want appointment. But we know the following. Then if V is any vector here, then we can written like this: 1 to 1, right? En for some T1 up to En in K, because this is the basis for V moves at any vector in V can be written like this. So what is AB? Well, this is A head of E1, and but A is linear, so A head of B is just since it is linear, it is C1 times A head of E1 and up to Cn, A head of En. In other words, it's just C1 times F1 up to Cn times Fn, right? So the value of A is determined, right? For a vector B, its value is determined uniquely. Why uniquely? Because these TIs are uniquely determined, right? A vector B can be written like this in a unique way. So this T1, C2, Cn are uniquely determined. Therefore, the image of this is uniquely determined. I am using the same CIs. Okay? Okay. No. This doesn't have to be a base. This linear map could be the zero map. It may send everything to zero. When all these Fi's are zero. Okay? I'm not excluding that. But this tells us what? A head is uniquely determined by its images on a given basis. If I know this F1, F2, F3, and so on, then I know what A is. In any other vector, I can use this gadget. One other thing, okay, this also shows the following. If you give me this basis and say that construct me a linear map so that that linear map sends A1 to F1, A2 to F2, I can do it just using what I have done over here. Okay. For the second statement, if beta and F1 are given, I said pre-assigned values, right? So I ask this, A of EI is equal to AI. And we ask if there is such an A cat. Yani ben şunu soruyorum burada. Bu bat elemanları verilmiş olsun. Bir de W'lara ne tane bekliyorum. So I am given a basis for B. And given arbitrary elements F1 to Fn in this vector space. They don't have to be a part of the basis already. Okay, they can be any elements. Maybe some of them are zero. The question is there a linear map sending EI to Fi for each R? The answer is yes. For a second, but I actually already showed you how you define it, right? I birden en ekledim. Are given yani bana bir basis verilmiş, bir de ne tane vektör verilmiş. Öyle ki bu basis elemanların görüntüleri bunlar olsun diye. Ama şunu bilmiyorum, böyle bir A var mı? Ben şimdi var olduğunu söyleyeceğim. So, the question is, is that such a head. The answer is yes. So that's the statement of the theorem. Yes. How? Well, I have to tell you what is the image of any vector. Take any view and write it as v equals C1, E1, Cn, En in a limit way. Okay. Finally, define a head of V. Ne kadar edeceğim? Şu pozisyonu C1 times F1 Cn times F1. Okay. Then this is a linear. Then one can check that. Project is linear. And of course, and a head of EI is that. A head of EI is what? Well, if I write here EI, then, for example, if I write here E1, then E1 should be 1 times E1 and 0 times E2, 0 times E3, and so on, because this is a unique representation of any vector, and E1 can be written as 1 times E1, 0 times E2, 0 times E3, and so on. And there should be the unique representation. And image of E1 will be what? Image of E1 is just, since it is 1, all of these are 0. Image of E1 will be E1. Image of E2 will be, no, image of E1 will be F1. Image of E2 will be F2 and so on. So this will be F1. Örnek yapalım mı bununla ilgili bir tane? Okay. So let me give an example of a projector. Okay. Now let V to be let's say R3. So this is a vector space over R, and S to be the following subspace. Okay, subspace. Okay, şöyle olsun. X, Y, Z such that X plus Y plus Z equals 0. The subspace. This is a subspace. Why is that? Because if I have two vectors whose coordinates adds up to 0, then when you add them up, you get another vector, but the sum of those coordinates will be just sum of the first. Okay, let me just write down. So first, this is the subspace. Why is that? So if we want, let's say x1, y1, z1, and V2 is X2, Y2, Z2. Then I have this X1, Y1, Z1 is equal to 0, and X2, Y2, Z2 is equal to 0. But then V1 plus V2 is just X1 plus X2, Y1 plus Y2, and Z1 plus Z2. Is this in S? So we ask this. Is this vector is in S, right? Is in S. Take a look. Well, I have to add its coordinates. X1 plus X2 plus Y1 plus Y2 plus Z1 plus Z2. Well, that is just, since addition is commutative, I can just, you know, change the places of X's and J's and so on. So I can write this as follows: X1 plus X, Y1 plus Z1 plus X2 plus Y2 plus Z2. Right? Well, this is just 0, and this was 0. So this one is done. What about scalar multiplication? Similarly, lambda times, let's say V1 is just lambda times X1, lambda times Y1, lambda times X1. And if you add these coordinates, so we ask if this is in S, right? Scalar multiple of a vector lies in S or not. Well, you have to add the coefficients up. Let's do that. Okay, so lambda times X1, lambda times Y1 plus lambda times Z1. That is just lambda times X1 plus Y1 plus Z1. But this is already 0 vector. Lambda times 0 is 0. So the answer is hence this is the subspace of R2. Aslında çizebiliriz de onun ismini. What is S? S is a subspace of R3. It's a subspace of vectors so that the sum of coordinates is equal to 0. Efendim? Yes, it's a plane in R3. Orijinden geçiyor, değil mi?
Hocam normalde diyoruz.
Tamam. Bir. İşte şurada. Şöyle. Bir yukarı çıkacağım, değil mi? Şu. So this is the normal vector of the plane. So it should be something perpendicular to this one. Yani nasıl olacak? Şu one normal vector. Böyle bir şey normal nasıl çizersin? Yani bu normale şey çiziyoruz. Çok yaşa. Şurada kolay da şuna normal yani şu olurdu. Değil mi? Evet, şöyle bir şey çizdim. Ben size anlatayım. Tamam mı? Efendim?
Gerçekten anladım.
Sağ ol. Nezaketen söylemiyorsun.
Yok gerçekten.
Okay. Now let's see how can we write down a projector. onto this subspace. What is the idea? First, I find a basis for this given. Find a basis for S. Well, S is not the whole vector space, right? It's a plane. It shouldn't be the whole thing. Can you give me some elements in this set? So you need to give me vectors whose coordinates adds up to 0. 1 minus 1, 0. Another one.
1, 0.
1, 0, minus 1.
0, 1.
0, 1, minus 1. Well, actually, this will be enough. Okay, this will be enough. These are linearly independent, right? It's clearly linearly independent. And if you choose any element, so if küçük olunca böyle söyleyeyim. If x, y, z is in S, then x plus y plus z is equal to 0, right? So z is minus x minus y. Hence, I can write the following: x, comma, y, comma, z can be written like this: x, comma, y minus x minus y. And I can write this as x, 0 minus x plus, okay, yes. What? 0, y minus y. I can write this, right? So what is this? Belki sizin verdiğiniz basis'i kullanacaksam böyle yazmak iyi değil. Değil mi? Burada 1, 0, eksi 1 var. Şu var. Y'yi yazsak, x'i yazsak daha iyi. Aferin. Eksiye çizme. Şöyle. Eksi y, eksi z, y z. I can write this as minus y, y 0 plus minus z, 0, z, right? And this is just minus y times 1, 1 minus 1, 0 plus minus z times 1, 0, minus 1. So your basis elements. This means what? This means that this set, is not only linearly independent, but it also spans S, right? Every vector can be written in terms of these two vectors. Therefore, this is the basis for S. Hence, this is 1, maybe 1 minus 1, 0, 0, no, 1, 0. Yes, is the basis for the plus. What is the next thing? We would like to extend this to a basis of R3. Now, we need to expand this to a basis of R2. How can we do this? I will to add another basis to this, another vector to this. R3 is three-dimensional. I have two vectors, so I need one more vector. And actually, it doesn't matter which vector we choose. As long as the set is linearly independent, we are okay, because any linearly independent three vectors will form a basis for R3. So I have this three vectors, 1, minus 1, 0. 1, 0, minus 1. Okay, give me another vector.
0, 1.
0, 1, minus 1. Hatta istediğiniz vektörü seçebilirsiniz. Toplamı 0 olur. Zaten minus 1 olmaz. That one doesn't work because that's also in the subspace. It shouldn't be in the subspace, so let's just this one will work. This is not in the subspace. I choose something outside. If you choose something inside, then you should have to stay in the subspace.
Küçük mü oldu? Tamam.
Bir ara verelim.